you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you ready to go?
Hello, it's Mr. T with a tutorial on finding derivatives of log functions. If you need a review on basics of logarithm functions, you can refer to my earlier video on logarithm functions. So today we're going to be focusing on taking the derivative of natural logs. There will be a future video that talks about logs of other bases. If we just have the function y equals ln of x, the derivative of ln of x is 1 over x. Now most of the time we won't just have a plain x here, but we'll have some expression. So using the chain rule, we'll have 1 over u times the derivative of whatever we're taking the log of the derivative of u. So let's look at a couple examples. So in this one, this is our u. So our y prime will be 1 over u, which is 2x, times the derivative of our expression, which would be 2, and that's going to simplify to be 1 over x. If we look over here, this is our u, so we have 1 over times the derivative of the numerator, which will be 4x. So we have 4x over 2x squared plus 4. We could GCF factor out a 2 in the bottom and then cancel out. So we would be left with 2x over x squared plus 2. Here we have a x in the front. We're going to need to use the product rule. Or v will be the ln of x, and v prime will be 1 over x. So when we cross multiply here, we get x times 1 over x, which would be 1. And then here we get plus the ln of x. And if we have this, we could rewrite this as x to the negative first power times ln of x and use our product rule again. So u prime is going to be negative x to the negative 2. And here we have, so should have had a line there. V prime will be 1 over x, which is x to the negative 1. So when we cross multiply here, we have x to the negative 1 times x to the negative 1. We add the exponents. And then we have this cross multiply. And we could GCF factor out the x to the minus 2. And then we could, again, simplify that by moving the x squared to the bottom. So these were basic ones. They didn't require any sophisticated work. Let's look at or talk about more complicated examples. And the key here is we can use our log properties to simplify the logarithms before we take the derivative, and that will make the process easier. So here I am going to rewrite this first by changing the radical to a fractional exponent, and then the log property allows me to bring this exponent out front. And then we get our answer here. If we had not thought to do that simplification, then our y prime would have been 1 over x plus 1 to the 1/2. And then when we take the derivative of our u here, we would have 1/2 times x plus 1 to the negative 1/2 times the derivative of that. And if we simplify that, we would get 1/2 x. Here we would be subtracting to the exponents. I'm sorry, this would be x plus 1. To the negative 1 power. which would then be 1 over 2 times x plus 1. So we get the same answer here, but it was more work than using our log property. So let's look at another one of those. So here we can use our log property where we can split this up into two logs, the log of x plus the natural log of x squared plus 1 squared, and then we can bring this exponent to the front. And now when we take the log of each piece separately, because we have a plus here, we get for our y prime, we have 1 over x, plus here we have 2 times 1 over x squared plus 1 times the derivative here, which would be 2x. So now if we simplify that, we've got 1 over x plus here we have 2 times 2x is 4x over x squared plus 1. Now we could possibly leave it like that, or we may, if we were trying to find critical values, want to get a common denominator. If we did that, we would have to multiply this fraction by x over x, and this fraction by x squared plus 1 over x squared plus 1. And we would have, on our denominator, we would have x times x squared plus 1. Whoops, extra parentheses there. And the top we've got, if we distribute here, we've got x squared plus 1 plus here 4x squared. And our final answer would be 5x squared plus 1 over x times x squared plus 1. And then we could proceed to try to find critical values or zeros. Now in this example, we're applying derivatives to find the relative extrema. So remember, we want to find y prime first. Now remember, this here is the same as 1/2 times x squared minus ln of x. So when I apply my power rule here, I've got 2 times 1/2 is 1, so I just have x minus 1 over x. And we want to set that equal to 0. So we could get a common denominator here. So if we multiply this by x over x, we've got x squared minus 1 over x for our y prime. And again, to find critical values, we're setting the numerator equal to 0 and the denominator equal to 0. So on the top we get plus or minus 1, and on the bottom we get 0. Now if we look back at the original function, the domain of the log function is positive numbers. You can't take the log of 0 and you can't take the log of negative numbers. So these numbers here are outside the domain of the function, so we don't even really need to look at those. So we're just going to be looking at this interval. So if we look at this, if we put, say, 0.5 into here, we're going to have negative on the top and negative on the bottom. I'm sorry, we'll have positive on the bottom because we're putting in positive 0.5. So we have a decreasing. And if I put a big number in here, we're going to have positive over positive. So we have a relative min at 1 comma. Now we have to calculate our y. So if we put 1 in here, our y value is going to be 1 squared over 2 minus the ln of 1. This will be 1/2 minus the ln of 1. The ln of 1 is 0, so we get 1/2. So we have a relative min at 1 comma 1/2. And our last example is an application problem here. We have a score where we are measuring the performance of students over time. So they take a course as a freshman year and then they never take it again, and they every 6 months are taking a test, and we're looking at the trend of their scores. If we made a XY table or here or a P table, we would see that over time their performance goes down, as you would expect. They tend to forget some of they learned. So we want to find here the rate of change. How fast are they forgetting the information? So we need to find P prime, because the derivative is our rate of change. So if we take the derivative of this, the derivative of 91.6 is 0. And here we've got negative 15.6 over t plus 1, and then times the derivative of the expression, which would be 1. So it's just negative 15.6 over t plus 1. So now we wanted to find our rate of change after 1 year, 2 years, and 4 years. So let's let our t here, and we'll evaluate our p prime. So we're going to do that for 1, 2, and 4. If we put 1 in here, let me pause this and bring up a calculator. Okay, so I've brought up our table and I've entered in our p prime. And we can use the table function here to fill in our table here. So we've got negative 7.8. And for 2 years, negative 5.2. And 4 years at negative 3.12. So their average on the test after 1 year is decreasing at a rate of 7.8 points per year. And then the second year, negative 5.2 and negative 3.12. So if we look at our graph of that, and we're interested over here. So our rate of change of information is higher negative here. So initially we're losing our knowledge quickly, and then it kind of levels off. So there's a core set of information we'll retain, but we lose some of the key aspects there during that first year. So I hope this helps, and good luck with deriving logarithms.
Are you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you ready?